Hello and welcome from Germany here to my showcase session, the LS Telcom showcase session, spectrum monitoring of higher frequency ranges, challenges and solutions. My name is Philipp Abel. I'm the responsible product manager at LS Telcom for our spectrum monitoring solutions. First to LS Telcom, we at LS Telcom have software, hardware, planning services, consultancy, and training for optimal spectrum use. We have our own spectrum management system, the MySpectra solution. So we have as customers groups, for example, national regulators or also industries or airports. Then we have our own spectrum monitoring system, our LS Observer solution, which I will introduce today in this session. Then we also have our network planning tools where we calculate, for example, propagation scenarios, where we do interference analysis. Then we offer consultancy for different topics like 5G. LS Telcom is based in Lichtenau in Germany, where I'm actually sitting now. We have worldwide offices, so we are a worldwide operating company, has customers worldwide. Currently, they are working around about 240 highly specialized employees at LS Telcom. Okay. Before I will start now my session, I will switch off my camera again to see you more of the slides in detail, and then for the question and answer part at the end I will turn on the cam again. You can always also during the session type in questions. I will answer them at the end of this session. Okay, let me turn off the cam and go back to my presentation. Okay, now today's topic is about monitoring of higher frequency ranges. To understand this, we first need to look at the traditional way. The traditional way of spectrum monitoring was to only monitor lower frequency because there was no demand for looking at higher frequency. You can see here on the left side a typical traditional monitoring station. It monitors lower frequencies up to HF or VHF. It's typically based on a heavy infrastructure, and yeah, you can see that has a big tower. It's based on a big tower, so you have a really big footprint for this. It's pretty cost intensive to install such a station, but at the same time, you only need a few stations per country because of the large coverage due to the low frequency measuring range. Typically includes direction finding functionality, an equipment room next to the mast, and it's in the traditional way manual operated, so there's no automation. So what I want to say here is you still need those stations, but due to the shift to the higher frequency ranges, you need different kind of monitoring equipment. And yeah, to have a look at modern monitoring equipment, we first need to look at the spectrum usage trend of the last 2 to 5 or even more years. So what we see is an increased spectrum usage in higher frequencies. More and more devices demand for spectrum. We have new emerging technologies like 5G or IoT, already good established technologies like LTE or Wi-Fi. These topics here leads to changes in the requirements for monitoring systems. So from such a traditional system, which you saw in the previous slides, we now go over to a modern monitoring system, which consists of small, flexible, and lightweight monitoring units, which are easy to install or to carry. A modern monitoring system means a high amount of sensors which monitor typically urban areas. A high amount because you monitor also higher frequency ranges where the coverage is pretty low. To capture everything, you need to have multiple stations, not only some like this traditional heavy stations. Due to the amount of station, a manual operation is no longer applicable. You need automation, you need networking of all the sensors, and the sensors need to be smart. There should be only a small footprint available for the sensors because you cannot install such heavy stations in a city. So you need to install them easily, like for example on rooftops or lantern poles. Yeah. Because you cannot capture everything with fixed station, you also need flexible equipment like temporary fixed station for measurement campaigns, some mobile sensors for drive test or emitter hunting or walk test. And you're still interested in the lower frequency ranges, but you're also especially now interested in the higher frequency range. So it goes from HF up to SHF, so 10 gigahertz and even more, yeah, like 18 gigahertz, even 44. We have even a model till 44 gigahertz. Yeah, now we come over to LS Observer. What we did with LS Observer at LS Telcom, we developed a monitoring system based on those modern spectrum usage trend. LS Observer is a sensor-based automated spectrum monitoring system, and I will now describe each single term of this definition. First, to spectrum monitoring. For those who are not so confirmed with spectrum monitoring, that this is a traditional spectrum monitoring view. You have a power versus frequency chart. You can see here the signal. It's FM here from 86 megahertz up to 100 megahertz. You can see the FM channels here. Down here, you have a waterfall chart, so the signals over time. Now we're here in the broadcast range, so there's permanently a signal on air. You see it here, a permanent line. Okay, but LS Observer is more than this traditional monitoring. We have features like automatic violation detection, where LS Observer can automatically detect some anomalies in the spectrum, like interference, transmitter failures, jamming, pirate transmitters, for example. And then if you have some issues in the spectrum, you can also locate the issue, the source of interference, the jamming source, for example. LS Observer is sensor-based, so a modern monitoring system needs to be sensor-based. We have here, you can see our portfolio. We have different sensors for different use cases, starting from the fixed monitoring unit for more permanent monitoring with all the transportable and portable equipment. And even we have a flying monitoring unit, a fully integrated drone-based system. LS Observer can be either, each LS Observer device can be operated standalone, but what makes it really interesting is to network all sensors together. If you have hundreds of sensors, for example, a countrywide monitoring system, you can network them all together. You have fixed station, portable equipment, mobile stations, and you can control them here remotely from a control center. As a modern monitoring system, LS Observer is highly automated. Our monitoring units permanently record the full frequency range of interest and stores it locally, so you can access whenever you want the stored data to make analysis. We have this automatic violation detection feature. Based on this, automatic alarms are generated if something is wrong, and then automatically the source of interference, for example, can be located with different methods. What does LS Observer consist of? So on one side of the hardware of our remote monitoring units, we also have our own direction finding system, which is very unique on the market. And then we have our LS Observer CMS, central monitoring software, which controls everything. And this combination is LS Observer and allows for a wide range of powerful features. So, beginning with the hardware to the remote monitoring unit, each of our sensors includes the same major internal parts. Beginning from the antenna to the receiver, or we can even integrate two receivers for parallel tasking with embedded processing power, so everything is processed locally. We have a communication modem for networking, and what's very interesting is that we have a large internal storage. With this large internal storage, the philosophy is LS Observer is to permanently record everything. So the spectrum, for example, from 9 gigahertz up to 6 gigahertz or even up to 18 gigahertz, you can permanently record on the local device. You do not need a permanent network connection. No data is loose. You simply connect to the monitoring unit when you want. For example, when you come to the office and at the morning and display or download the data of the last night. Besides storing the data, it's important that you can make use of it. So with LS Observer, you have multiple features to analyze stored data. You can use stored data in LS Observer to detect, analyze, quantify, and locate interference, which occurred in the past and is maybe even not on air anymore. You can set a reference baseline for future measurements in order to detect anomalies like interference, for example. And that means you have this automatic violation detection. You come at one site, measure 1 week, set this baseline, say, okay, this is my normal spectrum situation. And then when you come the next month, for example, measure again, every anomaly from this reference situation will trigger an alarm in the system. And with LS Observer, you can create with the stored data meaningful long-term spectrum usage statistic if you measure over several weeks or even months or even a year to support the spectrum management process. For example, to support it in assigning frequencies, reassigning, spectrum sharing, and so on. We have different versions of our remote monitoring units. Those are the standard version. You can see our widest version go from 9 kilohertz up to 18 gigahertz, so enormous frequency range covered with one receiver. And we've also modeled in our drone for microwave link measurements up to 44 gigahertz. So now individual to our monitoring units, we have here our fixed monitoring units, which is for 24/7 monitoring, indoor or outdoor. It can be standalone or remote controlled. So it permanently captures everything here locally on the local storage. You can also connect it to it remotely and look at the live measurement. It's very easy to install. You can directly mount this on the mast. That saves you in comparison to traditional systems, which where the receiver is installed on the technical room next to the mast. It saves you cable and therefore it saves you attenuation. So you have a lower attenuation with the FMU directly installed at the antenna. And you can see here, it's pretty easy to install. Here's such a semi-fixed installation, which is installed at a local airport here near our headquarters. It's our demo system, which I will connect to live in about 5 minutes. Then you can also connect it to lantern pole or here on a rooftop. Then the TMU is the transportable monitoring unit. It has basically two use cases. The first use case is you can put it on the trunk of the vehicle, make an antenna on top, and then you have a measurement vehicle. You can do drive tests, for example. And then the second use case, it includes battery up to 8 hours here, or can be powered from the grid. You can also use it for measurement campaigns, for temporary fixed measurements, like you can see here at the airport. So that means you place a TMU 1 week here on the rooftop, and the second week, for example, inside the terminal. So you can do measurement campaigns with it. It's pretty flexible. Then one smaller factor, it also includes a local battery, but not such a big battery like for the TMU. It's a protected portable unit. It's IP67 protected. You can either control it locally here from the screen to do on-site measurement, or just close it here, and then you can also operate it remotely for permanent measurement, also for measurement campaigns, for example. And then our portable monitoring unit, which is typically used for emitter hunting, like you see a homing operation with a directional antenna. That means you try to locate a signal source on the last meters here by turning the antenna. We have a homing mode here in our software, which gives you an acoustic feedback also, and a power bar, where it's pretty easy to locate such an emitter. Yeah, it's also possible to do indoor measurements like you can see here on the right side. Then to our drone-based system, the airborne monitoring unit. It's a fully integrated system. So everything which is observer, the processor, storage, receiver, everything is carried by the drone. And you can attach different antennas, like you can see here, a log periodic antenna, which can be also turned in polarization direction. For the drone-based monitoring unit, what is the use case for it? It's pretty interesting. We've done a lot of tests here. Just look at the spectrum. If you're on the ground and then fly up, you suddenly see signals popping up in the spectrum which you do not see on the ground. Yeah, it's simply that you fly any obstacles you have line of sight to the emitter. You increase the coverage of your monitoring system. You also minimize the measurement falsifications caused by reflections, for example. And you can also, if you fly up, you can turn the drone 360 degree to perform direction finding, so to know where a signal source comes from. Also, one use case is it's pretty easy to fly up with a drone in a microwave link to look if the microwave link is active, to view the power of the link, to view the frequency. That's why we have a special microwave link version up to 44 gigahertz for inspection of this. This is typically used by regulators or by operators. Okay, so also we have our own direction finding system to locate, to triangulate emitters. It's our AWA1XX automatic DF system with one antenna. We have different versions. One version, which includes direction finding and monitoring functionality, goes from 8 kilohertz up to 12 gigahertz, everything with only one antenna. Or we even have an 18 gigahertz version for direction finding only. This antenna consists of a multi-layer, multi-directional array of directional antennas, and for the monitoring version, there's only also an omni antenna included. So we have circular arrays of directional antennas. With this, we have our unique, you can either locate emitters live, so estimate the line of bearing, or which is unique here for this thing, is a DF time derivative technology. That means you can perform direction finding based on recorded spectrum scans. Yeah? And that means you can, for example, capture 24/7 a scan from 9 kilohertz up to 18 gigahertz. And afterwards, you can display the stored data, and afterwards for every frequency within this range, you can calculate the line of bearing for it. So you can subsequently perform direction finding. It's also with one antenna able to receive horizontally as well as vertically polarized signal. You can resolve multiple code channel signals. For example, if you have an interferer or wanted signal, you can also use a directional element of this antenna to perform monitoring, so to look only at a specific direction. For example, for border monitoring, if you want to know everything which comes from outside from the border. Yeah. It's available for fixed applications, like you can see, also for for mobile application based on a vehicle. Okay, this to the hardware. Let's go to our LS Observer CMS central monitoring software. LS Observer CMS is a pretty modern and innovative software. With a wide range of powerful features, there are only the highlights listed, from spectrum scan over demodulation, ITU compliant signal parameters measurements, IQ data record, automatic violation detection, data analysis, also include geolocation and direction finding feature, which I will introduce later with DF time travel, TDOA, and GROA plus. So CMS has a very powerful range. As we are limited today with this session, I can fill hours of this. I will show you some highlights of this session, and I'll also show you the software live in our demo system. First, to the operation modes. So you can either control an LS observer locally, or if they are multiple networked, centrally from a central control position. So you control remotely a fixed monitoring unit, for example, or that's interesting, also decentrally. That means you control from a portable monitoring unit, for example, a neighbor fixed unit to help you with triangulation. The communication is based on TCP IP. That means many communication formats are possible. For example, the public internet secured via VPN. Okay, so let us go live in the software. I'll switch over here. We've installed the LS Observer CMS software on a cloud computer so that everybody here from LS Telcom can access this to do online demos. And we're now here at the LS Observer CMS software at the monitoring system overview. There you can see all connected monitoring units, and then you can see their location on the map. Like you can see here, we have installed 4 fixed monitoring units around a local airport here in Germany. And now you can do measurements with all the units. To start a measurement, just go on measurement control, where again you can see a list of all connected monitoring units. And then to start a measurement, simply click here, for example, frequency range, and we want to display, interesting here, as we're at the airport, we want to display a bit ATC and a bit FM, for example. We go here from 80 megahertz up to 137 megahertz. Step width of the receiver, you can set up attenuation and gain and some receiver settings. Okay, and now you can see the live measurement from the airport system. We have here the power versus frequency chart. You can see here the FM signal. Here you can see the ATC signals. And down here you have the waterfall chart. So the signals over time. For the ATC, it's interesting. You can see here some signal is popping up and going down again. It's typically the pilot speaks and the tower speaks. You can always zoom in to analyze it in more detail. Click resample. So it's really user friendly here. Just go back to the measurement again. You can move the measurement, so it's pretty interactive here, the whole thing. You can also display maximum, average, or minimum curves. For example, the maximum is really interesting if you have such fluctuating signals. So you can see here, okay, the software remembers me here, there was a signal there. Okay, so this is the general spectrum monitoring view here. Then, if we want to do a recording, just hide this. We simply click here, recording, and now it offers you different options here, different data type. First, you can give the recording a name, for example. Then you can select the data type you want to record. We have raw data. It's all information provided by the receiver. Then we have a noise-free version where the noise is automatically eliminated. I will show it to you later. Then we have frequency channel occupancy. I also will have an example for you in the next step. And you can also have a long-term storage mode, which means you can aggregate scans if you want to compress data format. If it's enough for you, it will save you storage space. And the same is with overview data. That means you have overview of a certain time interval, like 8 hours or 24 hours, for example, if you do long-term measurement. So just click record. And now it's important. I can close my software. I can disconnect the connection to the monitoring unit. It will run the recording autonomously to the local storage. And later, can assess the monitoring unit again, stop the recording, and view the recorded data. Okay, before I view the recording, I will also show you to a second unit. Let us do the same frequency range here. Click start. And then if you have multiple units and you want to display multiple units in one chart, we have here the multiple measurement charts. So you can display two measurements here. For example, the raw measurement, you can give them different colors, and then you can see here the signal difference here. So you have multiple units in one diagram. Yeah, you can also display only the maximum curves of this. Can also zoom in and compare the levels. Okay, now let us assess the recording we just started. For recorded data, just go to monitoring data. Here again, you have a list of all recorded data types. For example, now for this unit, you can see it's still loading. It has a lot of recorded data on this. The storage of the FMU is enough to store up to 4 weeks of raw data, so of the highest data type from a point of view yeah, it's several gigabytes typically. And then we have noise-free data and FCO data, which are compressed data type. Those data types can be stored up to 2 years till the storage runs full. Okay, now you can see here that's the recording we just did. You can see the status is still recording, but you can display even if it's currently recording. So now for display, it's also interesting. You can either display the whole measurement or can limit it here. If you, for example, if you're a regulator, someone complains yesterday, I had problems in 120 megahertz band. Just limit your record to 120 and limit it to the time range where the interference was reported. So you can only analyze what you're interested in. For this, we want to show the whole measurement. And you can see again here, it's the raw data. It's what we just saw in the live view. With the slider, you can go here through time and see the spectrum for each position and time. You can also zoom in to analyze signals in more detail. Okay, now just have a look at it. Everything which is blue is now there's no signal. It means noise. So the level here, by the way, for those of you who did not see this, it's color coded. The red means higher level, blue means very low level. So deep blue here means simply noise, no signal. So our monitoring units internally eliminate the noise here from the spectrum and save a noise-free version. The noise-free version is a compressed data type, very easy to handle, and it saves you storage space. Like I said, it can be recorded up to 2 years of data. So here's the noise-free version, and you can see everything which was before deep blue is now white. White means no data. So the noise was eliminated. And by the way, it calculates you here the signal to noise ratio, which is a very meaningful parameter. Okay, Now to the frequency channel occupancy, it gives you the spectrum usage, the spectrum utilization over time. I have here a nice example from 98 megahertz up to 135 megahertz over a whole night. Yeah. Um, to the FCO, it's now FCO5. That means for 5 minutes intervals, the software calculates, okay, was that during 5 minutes permanent a signal on air, then the channel is 100% occupied. Was there only 2.5 minutes a signal on air, then it's only 50% occupied. The occupancy is here for each time step in this chart, occupancy versus frequency, and also in the waterfall chart, which is very meaningful here. So red means, again, highest occupancies of 100%. Blue means nearly 0% occupancy. Everything is white, is no data here. It's actually generated from the noise-free data. So what you can see here is on the left side, it's FM. If we have a closer look here, FM means broadcast for sure, 100% occupancy. So there's permanently a signal on air. Then it's white here. There's no signal. For example, for spectrum management process, you can now think about assigning here frequencies. And then you have here everything which is a bit blue here. It's the normal ATC, so sometimes pilot speaks, sometimes tower control speaks, and you can see the occupancy is it's about 39% or even lower, 10%. Here you have a red line with 100%. It's the ATIS transmitter of the airport. It's a permanent broadcasting electronic voice for the pilot, so it's permanently on air. That's why it's 100%. And then really interesting is here that if you look over time, is that during the night hours here at, you can see the time in the mouse over at nearly 12 at night, suddenly the occupancy will be lower. Yeah, it's the night traffic. There's not so much traffic. You can see it's pretty reduced, and then in the morning hour again the occupancy rises. This everything you can see from the FCO data. Then you also have overview data. Overview, for example, you can set up an overview for a certain time range. For example, for 1 hour, if I have here measurement over the night. Overview means you have the maximum, average, and minimum curve captured. Now for each hour one value. So you can see if I slide here through the time, you have one value for each hour, which is also a very easy to handle data type, very compressed. So for example, if you first want to analyze 1 month of data, you first look at the overview data to get an aggregated first picture. And then if you find something strange, you can look at the raw data and analyze it in detail. Okay, so let me go back to the slides again. Yeah, as I mentioned, LS Observer has multiple features. Just some highlight feature again, because we're running out of time. It's the automatic violation detection. How does AVD work? So for AVD, you can define a spectrum mask for each channel. Spectrum mask means you define the bandwidth of the channel. Then if you expect their signal, you can to define the expected level, so the normal level, signal level in this channel. And now if the signal exceeds those tolerances, so you can define an upper and lower tolerance where the signal can fluctuate, an alarm will be triggered. For example, if it exceeds the upper tolerance, there may be something wrong. Even a license holder violates again his license condition, or there's interference. Or if it's below the lower tolerance, there's an emitter outage, you will immediately get alarmed from the system. And you do this not only for one channel, but for all channels of interest. So for example, for this frequency range here, it's called then an AVD template. And then you can see here, I call it license emission, and here two unlicensed emission because they violate again the upper threshold. Important to mention is if you have a channel where you do not expect any signal, you can say the expected level is simply noise. And then every signal which will pop up in this channel will trigger an alarm. For example, if you have unlicensed channel or channels where it's forbidden that a signal will be on air, you will be immediately informed. Also, an example is jammer. Yeah, in airports we have a typical problem of GPS jammers, which are used illegally by truck drivers. If they are around the airport, there will be a jamming signal, and you can easily with AVD, a jamming signal will be immediately detected, and you will be alarmed, and you can take immediately actions against it. So how does AVD work? I have here a short screen capture. So we have this mask here. And once there's signal active, you can see there's an optical highlight. But AVD is made that's not somebody needs to sit permanently in front of the screen. So the optical highlight is one side, but you can also set up that you will get an email automatically when there's an alarm happening with all the alarm details. Also, you can view the alarm history at any time. So, for example, if you come the next day in your office and you can view the alarm history overnight where alarms, and you may be able to locate the emission source based on the stored data of the night. Okay, then as the last highlight feature, I want to show you how to locate emissions with LS Observer. The first option you have is to do direction finding. So with our direction finding antenna system, which is bigger than an omni antenna, but with this you can calculate a line of bearing. So with one antenna, you can calculate this line of bearing, which is illustrated here. And then you would need a second line of bearing for triangulation. Yeah, because if you only have such a line, the emitter can be everywhere. With the second line of bearing, you have an intersection point here, and then okay, my search signal is located somewhere here. Here in this picture, you have also third line, and the intersection is some triangle. To give the user better indication, you can also display here a heat map. Red means there's the highest possibility that the search emitter is located on this point. Yeah. And this can be done either with multiple, at least two direction finding antennas with fixed stations, or with one mobile device that you measure at two different locations, or you measure them permanently during driving. Unique is here that with our DF time travel technology, this can also be done on stored spectrum scans, like for example from 9 kHz up to 18 GHz. You can select any signal and calculate a line of bearing for this. The second option is time difference of arrival. With time difference of arrival, you don't need a direction finding antenna. It requires only a simple omni antenna. If I go back in the slides, I can show you such an omni antenna. It's simply this small antenna here. So this is better suited for urban areas where you do not have so much space. There it's difficult sometimes to install a direction finding antenna. TDOA means time difference of arrival. So the location calculation is based on the measured time difference of an arriving wave at 3 or more measurement stations. That means, for example, if you have your search signal is here, the arriving wave will be first at this station, second here, and third here. And based on this time difference, which is somewhere in the nanosecond ranges, you can recalculate it and can say, okay, here in my heat map, the search signal is located here. For this, you will need at least 3 or more stations which are connected to the network and can receive the signal of interest. T2A can only be done in LS Observer Live. So with the time wave and the next method, GRA plus, you can do it on recorded data. The time accuracy you need, because it's in the nanosecond ranges, you need a very high time accuracy. It's in LS Observer provided by the atomic clock of the GPS satellites. So all those units are perfectly synchronized here by this atomic clock. Okay, then to the short screen capture, how this is done. You can simply select live signal, double click, and then you can locate it. It will give you such a heat map. You can see it's developing here at the airport. By the way, the best result for T2A you will get if the search emitter is inside the polygon the sensors are opening. Yeah. Here we have a signal which is a bit outside the polygon, which also works, but it's far away, and then T2A will not work good because it's the geometric issues here. T2A works best for wideband signal. For more narrow band signals, it's from a physical side, it's limited. The uncertainty will grow, the time uncertainty. For this, it's better to choose DF or the next method, GRA plus, which I will introduce here. So what does GRA plus mean? It's basically the term gain ratio of arrival. That means the location calculation is based on the power difference of the search signal measured at 3 or more different locations. So for sure, if the signal source is far away from a sensor, then it will have a lower power at the sensor than if it's nearer. Yeah. If it's only free space. Yeah. Normally on the market in this method, the vendors say, okay, there's free space propagation, simple free space propagation estimated. But yeah, if you imagine here is a building or some mountain, some terrain, some forest between you and your receiver, your GRA plus result will be completely wrong. Yeah. So with LS Observer, based on our network planning tools, our experience in network planning, in wave propagation calculation, we include in this GRA. That's why we have here this plus. We take into account sophisticated wave propagation models, as well as we consider the topographic and clatter data instead of simply underlying the free space propagation method. And this makes the GRA method in LS Observer, the GRA plus method, to a very precise geolocation method. With GRA plus, you also only need omnidirectional antenna, so no direction finding antenna. You can also do this based on recorded data, and for this you simply need power values. Yeah, you can also do it based on noise-free data, which you can store up to 2 years in the monitoring unit of LS Observer, or you backup it permanently. Okay, just a comparison here, my last slide, between these geolocations technologies. So for triangulation, you have the DF antenna. You can do it sequential. That means with one mobile or portable device. Go at one location, do a measurement, go to second measurement, second location and do a measurement, or you can do it in parallel with networked stations. T2A needs to be done in parallel with 3 units at least. It only requires omni antennas. For GRA plus, due to the fact it can be also be done on recorded data, you can also do it sequentially with one portable device or in parallel with a networked device. Okay, so as of that, there are a lot of features missing, which I did not present today. I presented you some highlights. if you are interested in a detailed presentation of LS Observer, just visit lstelcom.com and request the online demo. Then I will give you a demo on details in LS Observer on everything you want to know. Just let us know. And then now I want to thank you for your attention, and we will come to the questions and answer part. Feel free to type in any question you want to know. I will now have a look at the chat. Let me turn on my camera again. Okay, so okay, I will just give me a second to go through the chat here. Yeah, yeah. The traditional way equipment is automated. Yeah, sure. There are also automated equipment in this way. I just want to say that earlier in years that those traditional stations which are for many years, even for 10 years or more in the country, are typically not automated and work remotely. Yeah. Yeah, the question is LS Observer TDOA based? Is it able to work together with AOA systems into a hybrid system? Yeah, as I illustrated you, it can do TDOA, it can do GOA, and it can do AOA, so this direction finding system. You have all three methods here, and you can also use it together because each method has its advantages, but also each is limitations. Like TDOA has its limitation with geometry and with narrowband signals. You can also do it in a hybrid mode. That means you can display a line of bearing, for example, together with a heat map generated from TDOA in LS Observer. In case we have existing system, does LS Observer database could work together? I do not know which database you mean, if you mean the spectrum management database. Basically, with LS Observer, we're pretty also experienced with customized project. Yeah, so we have realized customized project where we included already existing monitoring units as the customer side. So we integrated this in our LS Observer system. Always depends what kind of monitoring units you have and if the third party vendor of those units is open with his interfaces, yeah, and open to communicate with us. But we have the competence here of software developers to integrate already existing systems that the regulator, for example, can make use of them. Yeah, some guy here mentioned the ITU recommendation. LS Observer was developed according to ITU recommendation. We have also ITU signal parameter measurement feature in it to measure things like bandwidth based on the beta percent method or XDB method. What you mentioned here is receiver parameter measurements. So to measure IP3, for example, in this category, our receivers inside the monitoring units are all compliant to those ITU recommendations. So we orientate us on this ITU things. Mm. Do you have any documents related to interference guideline? How to solve this? Please kindly help me. Basically, interference, yeah, it can be caused by different kind of things. It can be a jammer, faulty emitter. It can be intermodulation products, and so on. If you want to know more about interference, if you want to learn how to do monitoring, how to solve interference, um, how to locate it, yeah, you can. We offer trainings here at LS Telcom. We have our own training academy, and then there we have general spectrum monitoring training, which is independent from vendors. So it's not only with our LS Observer. And there in this part, you learn a lot of interference and how it is detected, which kind of interference, and so on. Can you provide a result of a channel occupancy measurement in a PMR band? Yeah. What we've saw here, what I presented is frequency channel occupancy with no defined channel raster. Yeah, you can also, based on this, you can define a channel raster, for example, for the PMR, and then you will get in LS Observer a list, a table, a result for each channel. So for each PMR channel, you will get the occupancy value, for example, minimum, maximum, and average occupancy. I saw Richard already answered many of those questions. Thank you for this. Okay, I think I'm through the questions here. I hope I saw every question. If I missed something, I'm sorry. Then just if you have further questions, just write visit lstelcom.com and contact us with the questions. Also, as I said, contact us if you want to have an online demo on LS Observer, which will show more details of this system. Okay, then we're through. I want to thank you again for your attention, and then I will end our session. Thank you.